Greetings, Professor. I am Kunal Indore and I am here with my teammates Ankur Haritosh, Kvishi Liang, and Vishwanath Jayaraman. Today we are going to present our project for CS 5800 algorithms. Here we will explore solving the 8-tile puzzle problem using different algorithms. Before we dive into the algorithms, let's briefly discuss the 8-tile puzzle problem. This is a classic sliding puzzle problem which involves a 3 by 3 grid with 8 number tiles and one empty space. The objective is to rearrange the tiles from their initial configuration to a goal state by sliding them one at a time into the empty space. There can be 4 moves here. The empty space can move up, it can move down, it can move to the left, and it can move to the right. The move should be such that it doesn't go out of the 3 by 3 grid. As long as the move is within the 3 by 3 grid, we call it a valid move. The simplicity of the 8-tile puzzle problem and the challenge in nature has captivated puzzle enthusiasts and computer scientists alike. Our project centers around investigating different maze solving and pathfinding algorithms to tackle the 8-tile puzzle. Specifically, we will be exploring 4 main algorithms: the breadth first search, the depth first search, and the uniform cost search, and the Dijistra's algorithm. The primary goal is to evaluate the performance of each algorithm in the solving the 8-tile puzzle. We will start by exploring how BFS tackles the 8-tile puzzle problem. BFS systematically explores all the neighbor nodes at the present depth before moving on to the node at the next depth. For our puzzle, BFS exhaustively examines all the possible moves from the initial state level by level until it reaches the goal state. BFS guarantees the shortest path to the goal, but it may require a significant amount of memory to store the entire search tree. Now I'll hand over the presentation to my teammate Ankur, who will explain the DFS algorithm and its approach to solving the 8-tile puzzle problems.
Hello everyone, my name is Ankur Haritosh and I'm going to present the DFS algorithm for the 8-tile puzzle problem. So a particular state in the 8-tile puzzle problem is the 8 tiles of a particular combination. So basically DFS explores the search space by diving as far as possible along each branch before backtracking. So the search space is all these states of the 8 tiles. So DFS has a few branches, a few decisions to make on the um, branch that the DFS can take. And as, for example, in this tree, so a DFS can go and make a decision on a particular branch and keep on going till it finds a solution. If that particular branch is not a solution, the DFS would backtrack and go make another decision and go to another branch in search of a solution till it finds a solution. So DFS may find a solution faster than BFS by this branching and backtracking technique, but it does not guarantee the shortest path. However, DFS is memory efficient as it explores one branch at a time, whereas the BFS has a particular nodes of branches that it contains and stores at all times. So now Koishi will present the UCS algorithm next.
This is Kushi, and I will introduce the Uniform Cost Search algorithm, that is UCS algorithm. UCS explores the search space based on the cost of each move from the initial state, and this algorithm maintains a priority queue of all the nodes that have been explored. The priority of a node is the cost of reaching that node from the source node. It can guarantee the optimal solution, but it may explore a larger portion of the search space compared to the other algorithms. So in our problem, UCS works the same with Dijkstra here because of uniform the cost. This is because in the tile puzzle, every move has a uniform cost, that is usually 1. This means that the shortest path from the starting configuration to the goal configuration is equivalent to the one with the fewest moves. And both of the algorithms are cost-based exploration. This is different from the algorithm like A*, which use a combination of cost and heuristic. And both UCS algorithm and Dijkstra has an absence of heuristic. And they are also goal test. That means both algorithms will find the goal once it's the cheapest option on the frontier. Given that each move in the tile puzzle has the same cost, the first time a goal is selected from expansion, it is guaranteed to be the shortest path to the goal.
I'll be giving a quick walkthrough of the code that we've written as part of the algorithms project for the 8-tile puzzle solver. As you can see here, we have a Google Colab notebook in which we're importing all the different libraries, functions, and classes that we need to get our insights. As you can see here, we've imported libraries, have a puzzle node config state class in which we'll see the configuration states. We have a directions enum and algorithms enum respectively. We have puzzle node class, which has an initializer, which initializes it to a starting configuration, and we have a predetermined goal configuration, which is very simple, which is 1, 2, 3, 4, 5, 6, 7, 8, 0. We have a static method called getBlankPosition, which gets the blank position of the state. In this case, it's 2, 2 for the goal position. So row position is 2, column position is 2. We have another static method called move, which will perform certain moves to a starting configuration to reach another reachable position. We have another static method called isValidMove, which will check the validity of the move, and then we have a print puzzle static method which will print it out for easier viewing. We have another method called isGoalConfig, which will check if it reached the termination state or not. We have 3 different other kinds of methods. In this case, the first function is BFS style puzzle, which will perform the BFS action. The next we have is BFS, and then we have Dijkstra's. In this case, what we're doing is we're using a queue to keep track of different nodes and also having a visited set to keep track of positions that we've already visited. We are also keeping track of the time taken to perform this particular algorithm and also the memory usage. When it reaches the goal state, we are returning the moves that it has taken to reach the particular final state, also the execution time as well as the memory usage. Similarly, for the DFS, the same happens, except that we're using a stack to perform the DFS action. We are returning the moves, execution time, and memory usage as well for this too. Now we have Dijkstra style puzzle algorithm. So what this does is basically uses a heap or priority queue to keep track of the costs associated with each action. So in this case, because each action that we're doing, which is up, down, left, or right, is just one move, the cost associated with it is just one. And so this performance of this is similar to that of the UCS algorithm, which is why we didn't consider that in the performance statistics. So let's say, but there's one thing here to note is that let's say if each of the different directions have different costs associated with it, let's say the right direction costs more than the upward direction, the upward direction would have been prioritized more in this case. Yep. So moving on. Also, similar to previous algorithms, let's say if it has reached the final state, we return the move, execution time, as well as memory usage. Now, as part of the main function, we are returning, let's say we want to call algorithms BFS. We have a parameter inside that we call with algorithm BFS, which is the enum, and then it takes care of everything. And this particular function, which is a solve puzzle function, prints it out in a neat and visual format. So as you can see here, we can see the memory and time usage, and also the starting and ending configuration, and all the steps that it has taken to reach that particular final state. Similarly, we have done that for Dijkstra's and DFS as well. With regard to getting the performance statistics, what we're doing is we're generating the starting configurations randomly from the goal state by performing random moves to it, and we're getting a list of 100 random state configurations which are solvable in nature, and based on which we are finding out the mean, median, and mode for the different 100 sample size that we are using. And as you can see here, we are getting 100 starting configurations, finding out the different statistics, and plotting the graphs, as you can see, which you'll be seeing later in the further options of the present.
Yeah. Thank you.
Now I'm going to present the performance of these algorithms based on execution time and memory utilized. The average time and memory utilized over 100 random start configurations. So the execution time of BFS is the lowest because it contains a queue of nodes and operates by level order. Hence, it finds the optimal state at a faster time. The DFS time is the highest of 2.7 because of it explores all the branches and backtracks till it finds a particular solution. So there's a lot of exploring in DFS. And Dijkstra is in the middle of execution time of BFS and DFS. For the memory utilized, BFS is higher because again it contains at each level a queue of nodes of branches that is needed in BFS. For DFS, basically we do not need any memory utilization except the recursion stack because we are going at a particular branch at a time and not storing any other branches. And the highest memory is of Dijkstra. So here is a graph visualization of the performance of these algorithms. In the left graph, we can see that the time for the DFS is the highest, then is Dijkstra's, and then is BFS as expected. And in the right graph, basically we are showing the memory usage of these algorithms. So Dijkstra at all the instances of puzzle has the highest memory utilization. Then comes BFS, and at the last is DFS. Now, Qureshi will present the performance analysis comparison of algorithms of these algorithms.
Hello, this is Qureshi. Let's move on to the comparison of these four algorithms. So we have time complexity here and space complexity here. And we will see whether the algorithm is optimal. Here we can see DFS is not optimal, BFS, Dijkstra, UCS is optimal. As for the trade-offs, BFS will not be efficient enough for large puzzles because it will explore all nodes in the searching space. And DFS is easy to get stuck in loops. Dijkstra will be more effective with heuristic function, but in this way, it will turn to be a star algorithm. And UCS can be inefficient for puzzles with non-uniform costs. let's talk about conclusion. So in this page, BFS and Dijkstra, they are both optimal solution. That means we will always find the shortest path and it's complete. But the weaknesses are the same. They have bad time and space complexity. But for DFS, it will save memory for shallower puzzles, but it's not optimal. As we have mentioned before, UCS and Dijkstra work similar, so it will also find an optimal solution. That means we will find the shortest path based on move costs. But it has similar weakness, that is, it has exponential time and space complexity. Overall, UCS emerges as the most efficient algorithm for tile puzzle problem, and UCS strikes a balance between optimality and efficiency by guaranteeing an optimal solution. And UCS is well suited for puzzles of moderate depth and complexity. That's all. Thank you so much.